right. So hello and welcome everybody to another StaPH-B call. For those of you who don't know, StaPH-B is a self-aggregated group of bioinformaticians and scientists across the public health labs and other entities now. There's quite a few. I think we have over 100 scientists and over 50 organizations represented now on our calls. And it's pretty exciting to see how we've grown. I think that there are going to be some new people on the call today. I know that we've had quite a few new bioinformaticians kind of being brought on in some of the different public health labs, and just new people, new faces. So to those of you who haven't been here before, welcome. And to those of you returning, welcome back. Before we did get started, I did want to make a little announcement about the StaPH-B call, the last StaPH-B call that we held. And so I did record the video and I did upload it to the YouTube page, but unfortunately, it was flagged on the YouTube page. So that was the call where we had speakers from a company called Inovio, who was doing a vaccine development, come and give an update about their product and what they were working on and some of the kind of preliminary information that they'd seen. But so when we uploaded that video to YouTube, it was flagged as being potentially incorrect information, which I think it just has to do with YouTube being very, very strict with the amount of misinformation and disinformation that is coming regarding SARS-CoV-2 and the pandemic. And so they're kind of strict in that regard. And so I think that that's the reason that it was taken off. But I will work on trying to find maybe another site to host it on, because I thought that it was a really interesting call, and I know that a lot of people expressed interest in it and thought that it had some really neat information, and I thought that it had some neat information too. I'm seeing some suggestions in the chat. Maybe Vimeo, yeah, we can test it out and see if maybe there's another platform where we can host it, because I do know that people were interested in seeing it again. But so that is the kind of update that I have for now. And so I guess without further ado, I would like to introduce Eric Nawrocki, our speaker for today. Hopefully I said your name right.
Yep.
Eric is a staff scientist at NCBI, and he's going to be giving us a presentation about Vader, which is a tool that I know all of you are, if not intimately familiar with, at least familiar with hearing about. Especially as the pandemic has progressed and as we submit sequences to NCBI. I made some terrible Star Wars puns in my announcement about this particular call. I couldn't help myself, but I promise I'll refrain as we go forward. But I'm going to turn it over to you now, Eric. I think you've got your screen up and going already. So if you'd like, please take it away. And for those of you who aren't speaking, please mute your phones. We already had people regale us earlier about how there was a fun incident where people were talking when they weren't supposed to be. So I'm going to mute my phone now, and Eric, you can take it away.
Okay, thanks. And thanks a lot for the invitation. I appreciate the opportunity to talk about my work on Vader. So my plan is kind of to give an overview of how Vader works. There's actually some overlap with this talk. I don't know, maybe some of you were on a Spheres call. It was actually in October where I talked some about this. So there is some overlap, but then I'm going to go into some changes we made since then to deal with mostly the volume of data, and also a little bit about where we're hoping to go next, or some future plans. So the motivation behind Vader is really to help out these soldiers at Genbank that we call indexers, who are in charge of, they're kind of the gatekeepers of all the data that comes into Genbank. And so when data comes in, they're in charge of making sure it's the type of data that the submitter says that it is, and that it's high quality data and there's not mistakes in it. So that's a big job, especially considering how much data is coming into Genbank. So there's been a lot of attempts to try to automate this as much as possible, and Vader is essentially one of those attempts to help these indexers deal with a huge volume of data. And so we published this tool in 2020. There's a lot of people who worked on it. Alejandro Schaefer was my supervisor when we started. He's since moved to National Cancer Institute. And Nada Hatcher and Rodney Brister are part of the virus team at NCBI. Linda Yankee is the main indexer in charge of dealing with incoming sequences. Eileen is in charge of the Genbank team at NCBI. And Laura was a summer student that worked with me. So there's a lot of people who have worked on it, but I'm the main developer. And the kind of design of it is to be a general tool that we can use for different types of virus sequences. And it uses a reference-based annotation. So we use ref-seq sequences, but it's actually designed to be able to use alignments instead of single sequences, so profiles. But we've mostly used it in the single sequence as a reference. So for SARS-CoV-2, it's NC045512 is the main ref-seq that we use, but we do have alternative models. But each time a sequence is annotated, it's based on a single reference sequence that the annotation is done. We originally designed it so it was before the pandemic. SARS-CoV-2 didn't exist. So we designed it for dengue virus and norovirus initially, but actually pretty early in March, we started using it for SARS-CoV-2. So the way that it's set up is when sequences come in, they're automatically run through Vader if they're norovirus, dengue virus, or SARS-CoV-2. And Vader makes a call on each sequence, whether or not it passes or fails. And that's a simple, binary call, but it's actually pretty flexible. There's many different reasons a sequence can fail, and the user can change the thresholds and whether or not each of those checks causes failure or not. So we try to make it flexible so it could be used in different ways for different viruses. Sequences that fail, sequences that pass that have none of what we call fatal alerts. So Vader looks for many different kind of unusual features of sequences. And if it doesn't find any of them, the sequence will go into Genbank. If it does find some that we call alerts, and we specifically don't use the term error because it doesn't necessarily mean there's something wrong with the sequence. It just means that there's something about the sequence that we don't want it to automatically go into Genbank without an indexer looking at it. That's harder to do when you're getting tens of thousands of sequences, but that's the idea. And so any sequence that has one of these fatal alerts then goes to an indexer. And it's kind of a little more complicated in that some sequences, the alerts are so obviously bad that it'll automatically go back to the submitter with some explanation, as opposed to the indexer needing to look at it. But some of them, the indexer will look at it and then communicate with the submitter as to why the sequences are not being automatically put into Genbank. But some of them, the indexer will say are fine, and they'll be, we call it, pushed into Genbank by the indexer. And I meant to say at the beginning, if anyone has any questions as I go, just feel free to jump in. So now I'm going to try to explain kind of how Vader works. So when we have, this is an example using a dengue, one of the dengue ref-seqs, and the ref-seq has this annotation of a bunch of different features. They're shown up here. Dengue has a single CDS polyprotein that encodes a polyprotein that is cleaved into many mature peptides, and all of those are annotated on the ref-seq. Some of them actually overlap with each other. There's also some structural RNA regions, stem loops, and even a non-coding RNA. So these, non-coding regions, but they're still annotated as features. And so the Vader model has all of this information as to basically just where these features are on the sequence and obviously what the sequence is. And it then uses all that information to validate and annotate other incoming dengue sequences. So does that over 4 different stages, and I'll briefly explain each of those stages. And the reason we have these 4 stages is that we can identify different types of alerts at different stages based on how those stages use slightly different algorithms for looking at the sequence. And so those algorithms are more kind of adept at identifying certain problems than others. And so the first stage is the classification stage. Each input sequence is compared against each model in the library of models. So we have 4 dengue models. There's, I think, 11 norovirus models. There's 3, it's actually changed. I think there's 3 SARS-CoV-2 sequences or SARS-CoV-2 models. So when a sequence comes in, it could be compared against all those sequences. And then the one that gets the highest score is we call it the best matching model, and it's then used in all the remaining stages. So at this stage, there's certain problems you can identify that result in alerts. So if none of the, for example, if none of the models have a high scoring hit, that means that we don't know what the sequence is. That's a certain type of problem we call no annotation. If it's actually hard to tell which model is the best, so if the scores between the 2 best models is really similar, that can indicate that we're not really confident which model should be used. So that's another type of problem that can be identified. And then in the next stage, we call it the coverage determination stage. It uses a BLAST-like algorithm, local alignment. So it takes each sequence and compares it against the model, looking for local matches with respect to the sequence and the model. So typical case, if you have like a full-length sequence, you expect one very long match across the full sequence and the full model. You could also have a shorter sequence like S2 here, where the full sequence is still covered by the model, but it's partial. So those are both kind of expected cases where nothing unusual has been detected. But you could have other cases where you have extra sequence at the beginning or end that doesn't align well to the model. So those are specific types of alerts that get reported. You could have a case where there's multiple hits where there's a region in the middle that's not covered. That's a different type of alert. You could have a case where the hits are kind of out of order with respect to the sequence in the model. So like the beginning of the sequence matches to the end of the model and the end of the sequence matches to the beginning of the model. That's unusual, but it does happen. And so those are the types of things we can detect at this stage. And then in the next stage is the alignment stage. So now instead of allowing local matches with respect to the sequence, we force an alignment of the full sequence against the model. It doesn't have to align to the entire model, but it does have to align the entire sequence. So, and then based on that alignment, the reason we need to do that is we want to map the features from the model onto the sequence. So once we have that alignment, we can very easily do that. And in this stage, there's additional problems we can find. So for this example up here, S5, we have a case where the boundary of this mature peptide actually aligns to a gap in the model. So that means we're not really sure about that position of that mature peptide. So we can report that as a problem. If we try to translate a coding region and we find an early stop codon, that's another type of problem that we can identify at this stage. And then finally is the protein validation stage. So this was actually implemented by my supervisor, initially Alejandro. So the idea here is basically just another check on the coding potential of CDS regions. So we translate all the predicted CDS and compare it against the reference proteins from the reference sequence using BLAST-X. And we expect that that full length translated CDS should match completely to the reference protein. We might have a case where it does not, and that might be indicative of an early stop or maybe just a frame shift that causes that amino acid sequence not to match the expected protein sequence. We can also identify things like insertions and deletions, again, at this stage. So that's kind of an overview of how it works. The idea is basically we're trying to identify unusual things in the sequence that if none of those unusual things get identified, we're pretty confident the sequence is fine and it'll automatically go into Genbank. You know, some of these things are unusual, but we might want it to be okay. And so they don't actually cause the sequence to fail. And again, all of that stuff is kind of tunable by the user. And we change that actually somewhat frequently when we find that some checks are too strict when we use it in Genbank. So I'm going to switch gears and talk about the use for SARS-CoV-2. So this slide shows the number of sequences that got deposited in Genbank, SARS-CoV-2 sequences in Genbank. So in the first 6 months, I guess since first 6 months of 2020. So in January, there were only 33 sequences. In February, there were 68 added to make 101 total. So the gray bar is the total and the black is the per month number. So the numbers were pretty low. We started using it, Vader, in March when Linda couldn't handle looking at each sequence individually, or we wanted some automated way to do it. Vader isn't really designed for sequences as long as SARS-CoV-2 because of the computational complexity. It works fine for norovirus and dengue virus. Norovirus is about 7 KB genome, dengue is about 10 to 11. But when you go up to 30 KB, it gets really slow. So to align the single sequence with version 1.0, which is what we published on for norovirus and dengue, is about 5 minutes per sequence, and it can take up to 64 gigs of RAM. And again, it's just because of the complexity of the algorithms we're using. So that was okay when you have a couple hundred sequences, but it wasn't ideal. And when we got to thousands of sequences, we kind of realized right away that we needed to make it faster. So in addition to making it faster, there's another issue with SARS-CoV-2 sequences that caused a problem for Vader, and that is that they have a lot of ambiguous ends. So I guess the way people do assembly of this, when there's regions that don't have high coverage, they fill in with the appropriate number of ends based on the alignment to the reference. And that's just way more common in SARS-CoV-2 than in the other viruses we had looked at. It's not that bad if you look at overall percentage, only about 1% overall. But if you look at stretches of ends, about a quarter of the sequences have at least one stretch of 50 ends or more. And the reason that's a problem is because the whole annotation pipeline is based on sequence similarity. And if there's ends, it's just very easy for it to not know what to do because it can't rely on this expected similarity. And so there's just issues that come up. So we came up with a way to deal with that that seems to have worked pretty well. And that is, it's very simple actually, and that is just to replace those ends with the corresponding nucleotides from the ref-seq. So when we get a sequence, we first just blast it against the ref-seq, and we might have where the regions of ends are, you would just have gaps in between multiple blast hits. And so we line them up and we ask the question, does that region of ends, is the length of that region of ends the same length as the missing region in the ref-seq between the two hits? And if that answer is yes, which it usually is because of the way these sequences have been assembled, we just replace it with the ref-seq nucleotides. Then we pass it to Vader as if that was the sequence, and it does the annotation based on that. But then the sequence that goes into Genbank of course, has the original ends in it. And that seems to have worked pretty well in general. So that was one issue we had to deal with. The other is the speed issue, I said. So 5 minutes per sequence does not do well with high throughput. So we came up with a way just to exploit the fact that these sequences were so like unbelievably similar to each other. So typically 99.5%. With dengue virus, I mean, it's been around a lot longer. The average identity in dengue virus is around 90%, at least at the sequences I've looked at. And norovirus is maybe even a little lower than that. So 99.5 is really, really similar. And the algorithms we're using in Vader are kind of overkill. So BLAST-N, which is a much faster algorithm, but potentially less accurate for divergent sequences, works perfectly fine for SARS-CoV-2. So we went to BLAST-N, which is much faster. And what we do is we look for the longest ungapped region in the BLAST alignment. We kind of accept that alignment as correct. So we know this is ungapped, and then we only actually do the more expensive alignment steps at the end of the sequence where the BLAST alignment didn't cover. And so the reason we can't just use the full BLAST-N alignment is because BLAST-N does not like guarantee that it'll align the full sequence. And Vader set up to have, at that alignment stage I mentioned, to align the full sequence. Otherwise, it can't do the annotation mapping. And so the way we decided to do it is just pin the alignment where BLAST-N gets it ungapped, and then redo the alignment at the edges and join them together. So we're guaranteed to get the full sequence aligned. And that makes it a lot faster. So typically now, instead of 300 seconds, it's about 2 seconds per sequence. And it takes much less RAM because BLAST-N is more memory efficient. But the problem is some sequences, that region, especially if you have a sequence with a lot of errors in it, so like a bad sequence, quote unquote, this ungapped region might be very short. And so then you're basically just going back to the aligning the full length sequence the way we used to do it. And so it's not quite as slow, but for these quote unquote bad sequences, it's about a minute per sequence, and it still takes this large amount of RAM. But in May and June, when we were getting thousands of sequences, this was totally kind of workable. So if we look at how long it would take to process 5,000 sequences, for example, with the old version, if we dedicate 20 computers to it, it would take about a day, whereas with the new version, it would be about 15 minutes. So it was much better, and that worked. That was good enough for several months. So now what I'm showing you here is how those numbers went up since June 2020. So this was June, and now I think it was like December. It was December when we started to hear that the sequencing was really going to ramp up a lot. And this was right after B117 kind of took over in UK, and the UK got a lot of praise, I would say, for having good surveillance. And I remember reading in the newspaper that the US comparably didn't have as good surveillance. So there was this big push to increase the sequencing, as you all know. So in December, we started to hear that we were going to get a lot of sequences, and I started to get emails from people high up at NCBI saying, this is, we're going to get a lot more sequences. Can Vader handle this? And so I got basically I had to start working on the problem again to try to make it faster because people were concerned. And actually the big concern was with this 64 gigs of RAM requirement. So they wanted to put Vader on the cloud, and there's really just no cheap way to put something on the cloud if it takes 64 gigs of RAM. And so that was their big concern. So we had to try to address that. So the way we did that is pretty simple strategy, was to take the real memory hog and the slow program we were using called CM Align, replace it with a program called GL Search that also does this global alignment. So unlike BLASTn, we're guaranteed we get a full length alignment, and it requires much less RAM. So now 2 gigs of RAM. We just had to write the code that would call that program and then, parse the alignment and kind of slot it into the Vader code. And so once we did that, we were then guaranteed that aligning a sequence would only take 2 gigs of RAM. And that really opened up the door for multi-threading, which allowed us to go faster. So Vader actually processes each sequence completely independently. So it's what's called embarrassingly parallelizable. So you can basically just split up, and like if you have an input file with 150 sequences, we just split it up into, let's say, 16 chunks of 10 sequences each. That's actually the number it defaults to. And then if we have, let's say, 8 CPUs, we just give 2 chunks to each of those 8 CPUs, and it will process 1 chunk at a time. So it limits the RAM usage. Actually, it doesn't even need to store any more data than just 10 the data for 10 sequences at a time. So all the annotation data, stuff like that. And then it writes it out to disk, and then it moves to the next chunk. And then we just have to read all that information from disk and merge it. And basically at the end, it's like you just process 1 chunk, it's just merged all the 16 chunks together. Hopefully that made sense. So it's just very easy to do if you can split it up, and that limits RAM and makes it a lot faster because we can do basically it's 8 CPUs running at once. And so when we do that, we got down to, this is now Vader version 1.2, which we released in April. And that now can process about a sequence every 0.3 to 1 second if you use these 8 CPUs, and it's 2 gigs of RAM per thread. And that allowed us to deal with this increase in volume. And the people above me at NCBI were happy with that because it didn't have this large RAM requirement anymore. And we were able to deal with all this data. We started getting hundreds of thousands of sequences a month. And if we look at how long it would take to process 100,000 sequences, with the original version, it would have been 20 days, and now we're down to about 30 minutes. So it is manageable. Oh, sorry. So I just talked a lot about kind of optimization and speed increases, but we did do some more qualitative improvements along the way. So December 29th was the first B117 sequence in Genbank from the US. And we did, that sequence actually failed Vader. It has a shorter Orphate CDS that, looked like an early stop to Vader, so it failed it. So the way we dealt with that was to make a new model based on B117, and then sequences that come in that are B117 typically match better to that model than to the original RefSeq, and so it gets annotated with the shorter Orphate. And so that took about a week, so we were able to adapt to that pretty quickly. That was basically testing to make sure it didn't break anything else. Then in February, we had noticed that many of the Orphate was the CDS that had the most problems, where sequences would come in and fail because of problems in Orphate, but then the submitters would say that they trusted those sequences. They had good read coverage. And so we made a decision to basically say that Orphate was expendable. The way that we handle it in Vader is any fatal alert for Orphate just doesn't fail the sequence. And so it instead changes Orphate into a MISC feature in the Genbank annotation instead of a CDS, but the sequence will still pass if that's the only problem. And then in April, I told you we released this new version. At the same time, we released a new model for B1525, which has, I think about 90% of the B1525 sequences I've looked at have a 49 nucleotide deletion at the 3' end of a stem loop feature that we annotate in Genbank. And that feature just gets deleted completely. And so it would fail Vader. And so we made a new model for that. I wanted to say something about spheres. So we were really helped by spheres a lot. We were able to, inform people when we made updates, but also get a lot of feedback. We put a lot of effort into making Vader portable, as kind of, it's not perfect, but it is portable and can be run locally by labs before they submit their sequences. So they can see if there's problems with their sequence, basically if the sequences would be accepted into Genbank. There's a Docker container that adds to this portability, and I wanted to thank Curtis, who I think is on the call, and Anders for their work on that. That makes it even more portable. And again, this community just really allowed us to get feedback about when there were problems with Vader, and so that was very helpful. So the next version that we're planning on releasing, I'll just briefly mention what we're planning on. So basically went through a large set of sequences that we have collected that failed Vader, but the submitters said that they believe they were good sequences and should pass. And we found common problems, not unlike what I was talking about before with Orphate. There were some problems, like Orph3A has a very common early stop codon. And we were considering trying to deal with all those specific problems. And it would have to be a new feature in Vader to do that. But we did talk to the CDC, and we have decided to go the route of just, for these other non-essential CDSs, to allow them to have fatal alerts and just become MISC features like we do for Orphate. And that will probably handle most of these sequences that are failing Vader, but have good read coverage and everything else. And so you'll notice, Spike is not on here. So these are all non-essential proteins. So we also got some feedback from spheres as to the error messages not being kind of precise enough or useful enough. And so I've gone through and tried to improve that. So for example, this is one of the output files from Vader. We now have these additional fields that have the sequence coordinates for every problem, as well as the model coordinates. And this model coordinates is what was really missing for many of these error reports. Because that's what you kind of need if you're going to go back and look at alignment. They tell you where it's going to align to the reference. And so that's what at least a few users had requested. We have documentation on this that I've added. It actually took quite a lot of time to add this documentation. Hopefully it's useful. For each of these errors, we now explain what these fields mean kind of more specifically. And there's examples that are, I made this toy model where we show examples, and hopefully those are helpful if anyone is looking to understand these. So just in the last couple of slides, I did want to point out, we've all been, I don't know what the word is, crazy about SARS-CoV-2, but there are other viruses. So, and we did design Vader to be useful for other viruses. So we hope to expand it to other flabby. There's a type of other flabby viruses, Ecclesi viruses, and hopefully, continue to expand it to be used for other viruses. It does take some work per virus to kind of get the testing done, especially at Genbank, to make sure it's not, working well. But hopefully it will be continued to be used and expanded. We actually even use it for non-virus sequences. So the COX-1 is a common gene that's used for animal phylogenetics, marker gene. And Vader, we kind of adapted Vader to use it for that. And finally, there is some documentation on, all the documentation for Vader is on GitHub. I just wanted to point that out. I can share these slides if anyone, or you can just Google GitHub Vader. And then that's it. I just want to acknowledge that there are a lot of people at NCBI that have helped with this project. And Vader relies on a lot of external software. So Sean Eddy, who developed Hammer, Infernal, and Easel, those are all used by Vader. William Pearson developed FastA along with Michael Farrar. That's that program GL Search that is used for SARS-CoV-2. And again, Curtis and Anders for making the Vader Docker image available. And so thanks for listening, and I'm happy to answer any questions.
All right, well, thank you so much for the presentation. That was great. It's really interesting to see how this program kind of evolved and where it was. And I know I remember back in the beginning when we were first heard about Vader and how it was being used at NCBI. A lot of people were really kind of daunted by the memory and kind of the resources that it took to run. And so it's really interesting, I think, from our perspective to see, you know, where it's come from and how it's kind of developing and going forward. So I had a couple questions, and so I always like to start off with like a question or two, and then we can see if the audience has any questions. But I was just wondering, so you kind of went over it a little bit in your talk, but I was wondering if there's like a specific cutoff when you modify the model to say like, oh, you know, this is maybe not something that we would want to flag sequences for. Is there like a specific kind of way that you look at different alerts, or is it just kind of like an aggregation of a bunch, and somebody just kind of like looks and sees a pattern, like, oh, you know, a lot of these sequences are being flagged and it looks like it's due to this particular reason?
Yeah, more the latter. So there is no systematic way for us to do that. So for the next version, we're gonna be much more lenient on those non-essential proteins. So basically, like any problem in those will not flag a sequence and prevent it from being annotated or deposited in Genbank, but it'll just mean that those CDSs are not annotated. And we've kind of, yeah, we see it. I mean, early on, it wasn't, it's funny. I mean, because early on there was most of the mistakes were mistakes, but now, you know, as mutations have accumulated, it's different. So we're trying to adapt. I mean, and so, yeah, but there's no systematic way. Linda just has to look at it, and if she has some problem in Vader she wants me to fix, she'll tell me. But yeah, the route we're going now is just to misfeatureize them.
All right. What kind of steps should people do if they run Vader and it comes back with some of those alerts and things like that that would maybe not let it pass through to like Genbank or those kind of things? Is there any sort of like troubleshooting that you guys recommend, or is there any tips and tricks you can give from the experts?
Yeah, so I mean, part of the motivation for the extra information about like the positions of the problems was feedback we got from users who were kind of overwhelmed by the data and just didn't think it was, or the error messages, and didn't think it was precise enough. They didn't know how to look at the problem. So hopefully those positions, and that's why I made those examples to try to explain how to interpret that data. It's still a lot of information. I mean, I think it's a difficult problem because we're trying to avoid, you know, artifacts in the sequences from getting into the database. And so like, you know, sequencing errors and things like that. And so, but it's very difficult to tell those apart from natural variation. So if it's like a frame shift and, you know, in the spike protein, that's pretty, you know, that's different than if it's, you know, early stop that truncates one of the non-essential proteins by 3 amino acids. So it kind of depends on yeah, I mean, you have to know like what's essential and what's not. And so hopefully that extra data will be helpful at pointing people what to look for. One thing I didn't mention that NCBI recently did, it's actually not within Vader, but it's very related, is to allow sequences that fail to just automatically be removed when people submit sequences. And so all the sequences that pass automatically go in, but the sequences that fail don't prevent those other sequences from going in. So yeah, so I meant to mention that before. That's why I said it. But no, I mean, not too many tricks. I mean, when I look at these sequences, it does take a long time to look at even a single sequence. I try to make the error reports informative, but I think it's challenging.
So there's, it's basically just like a team of people who, whenever these sequences kind of get kicked back from Vader, they're going through and looking at these different things and then responding back to the people and giving them back. Is that kind of how the process works?
So there's really one person, Linda, who's in charge of most of the sequences. If she's like she has a day off or something, there's one other person, his name's Vince Calhoun, who helps, but it's mainly Linda. The idea is that early on, when there were dozens of sequences, you would look at each individual sequence that failed and communicate with the submitter. That just gets harder and harder when there's thousands and thousands of sequences. We've always tried to say, if you have a sequence that fails, that you are confident is legit, doesn't have any problems, please write back and explain why. And that is, I refer to it, I think that we had a list of about 1,000 sequences that Linda had compiled like that when she looked at them, she pushed them into the database. And so when I was after we did the release of the Vader 1.2, which made it a lot faster, the next thing on the to-do list was to go over that list of 1,000 sequences and try to see if we could improve Vader to allow them to pass. And what we eventually decided to do was the misfeaturization of the non-essential proteins, because that basically all of those problems were in the non-essential protein.
So do you recommend people to run Vader beforehand, before submitting sequences to kind of, and if they pass, then submit those sequences to you guys, or does it really matter?
We definitely recommended that before this auto removal change. So now if you submit sequences, the ones that so before that, if you submitted a bunch of sequences, even one failed, none of them would be deposited into Genbank. And so we got a lot of feedback that, that's not the best way to do it. You should allow the sequences that pass. And it took us a while to kind of do the engineering, but eventually that happened. And so that's how it is now. If you can run Vader yourself, it can save you some time, but if you get errors, and basically I would say that's true, if you get errors and you have the time to look at them, then you can maybe learn why those sequences, if those sequences are bad, or something informative from that. But it's basically, if you have the time to do that, then yes, I think it's a good idea, but I can imagine not everyone does.
Mm-hmm. I think we've got a question in the chat. It says, so if we have ORF errors, they may not be fatal errors and be able to be uploaded?
Right, so that's true. So there's some errors that are not, okay, so if you get a sequence that failed, if you try to submit a sequence and it did not get submitted because of a failure in the Genbank submission portal, that means that was a fatal alert. What I was talking about before is we're going to change that, what the fatal alerts are for some of the ORFs in the future, probably next month that will happen. And so then sequences in certain alerts in certain ORFs will no longer be fatal. And so if you resubmitted that sequence and the alert was in one of those ORFs, then it would go in. But we're working on that now. It's not ready, probably then by the end of next month.
Okay. Well, I don't want to hog all the chat here. Is there any other questions that other people have? Does anybody have anything they'd like to ask? Oh, looks like there's another question in the chat.
So yeah, I see that.
You got it? Okay.
Or sorry, I'll read it. So ideally, does Vader create a new model for each SARS-CoV-2 variants? Ideally not, actually, because so we want the fewest models that will allow all the good sequences to pass. So the variants are actually the only time we need to make a new model for a new variant is if it has like a CDS that is shorter or longer because of stop codon mutated or something. And actually there's very few of those. So B117 was one of them. B1525 I mentioned had a stem loop that got deleted at the end. But if you use just the NC044512 model, and then you run it against like consensus sequences of all the variants, basically all the other ones pass. So if they pass, then we don't really need a new model for it. So it's only when a new variant comes up that fails Vader, the current models, then we have to make a new model.
Out of curiosity, how many models are there for SARS-CoV-2 now? Is it just those 3, or are there a few more?
No, I should really know this. I think there's 3 or 4. Well, no, B15, there's a 4th one, right? There's 4, sorry. So there's one that there's a common mutation that extends Orphate by 4 amino acids that we made a model for very early on, actually before we did the started being more permissive about Orphate. So that model has stayed in. So there's 4. So there's the original one that 4 amino acid longer Orphate. There's a B117 model and there's a B1525 model.
Interesting. Is that kind of typical for the other viruses that you have as well? Do you have like multiple models for each of those?
We do, but it's very different actually, because those models are like these SARS-CoV-2 still all the sequences are 99% identical, whereas norovirus and dengue virus have been evolving for so long that the average percent identity is much lower. And so, and the other thing is that there's not, I think all the proteins we annotate in norovirus and dengue virus are essential proteins. So I think a lot, maybe, we're trying to annotate ORFs in SARS-CoV-2 that are not essential. And so they're, much more likely to be mutated. And that's why we have to make these new models. Whereas, yeah, it's actually pretty different with SARS-CoV-2 just because it's only been around for a year.
Mm-hmm. So will you use the kind of like updates and the shortcuts for these other viruses as well, or will those pretty much stay as like if we wanted to annotate dengue, would it kind of be with Vader 1.0, or would it work well with the kind of like changes that have been made to accommodate for SARS-CoV-2?
We still use, well, we use the new version, but we still, we use kind of the old code, sorry. So the new features we've added are like, you have to add a command line option to use them. So for dengue and norovirus, we just don't use that command line option. And the reason is we've kind of tested them all on SARS-CoV-2 and they kind of exploit this high sequence similarity. And it's not really necessary actually for norovirus and dengue virus because the number of sequences we get is so low that you don't really need the higher performance.
Makes sense. And so I know that you had said that you were annotating mostly viruses, and that there were new viruses that are kind of being brought on, but then there were also, it looked like just genes in general that can be annotated. Is there, I guess, what's the way that I'm trying to say this? So I guess, what do you envision the kind of like scope of Vader being? Is it going to be eventually something that can annotate everything, or is it mostly you're going to stick to kind of like very specific use cases?
Its main limitation, not everything. So its main limitation is length. So it can't be used like for a prokaryotic genome. And we didn't design it for that, but we did. It is okay for like protein coding genes, maybe ribosomal RNAs, which are a really commonly submitted type of sequence. But there'll probably need to be a lot of changes to make that work for that. But mostly viruses, I would say.
Mm-hmm. So it looks like you've got a question.
Hey, yeah. Hey, Eric.
Hey,
just
Curtis.
curious. So you think the next version will be out in about a month-ish, around there, or a little bit longer?
Yeah, we were just talking about it the other day. I think we're aiming for end of July.
Okay, no rush at all. I just just want to prep for the next Docker image, and also I wanted to say thank you for not to talk down on Pangolin, but thank you for having a slower release cycle relative to Pangolin.
Oh yeah, sure.
But thanks for all your work. Really appreciate it. It's been a great tool for us to use. So thank you.
Yeah, great. Thanks for all your help too.
Mm-hmm.
How often does Pangolin do a release?
Like between Pangolin itself and all the dependencies behind it, I would say at least once a week, maybe once every 2 weeks. It's evolving rapidly.
All right. Well, we only have a couple more minutes left, so I can leave the chat open. If anybody has any more questions, feel free. I think I've gotten most of my questions answered, and I'm gonna stop the recording right now, just so that we can not forget about that.